Have you ever pondered the question, how can we measure the size of an infinite set? A seemingly paradoxical question, right? Welcome to the world of measure theory, the mathematical framework that enables us to make sense of this conundrum. To understand measure theory, it helps to start with the basics. Picture a line on a piece of paper. How long is it? You might use a ruler and say it's 2 inches long, but that's not the whole story. To truly understand the length of that line, we must dive deeper into the realm of the infinitesimally small. Think of breaking that line into 1,000,000 tiny pieces, each so small that you couldn't see them with the naked eye. Now imagine breaking those pieces into even smaller pieces and so on, ad infinitum. This is the essence of measure theory. It's a way of understanding size that goes beyond our everyday intuition into a world where the infinite and the infinitesimal coexist. Measure theory begins with the concept of a set, a collection of distinct objects. These objects could be anything, numbers, points in space, or even other sets. The measure of a set is a way of assigning a size to it. For a finite set, this is easy. The measure is just the number of elements, but for an infinite set, things get trickier. Consider the set of all natural numbers. It's infinitely large, but how large exactly? And how does it compare to the set of all real numbers between 1 and 2? These are the questions that measure theory seeks to answer. The key to measure theory is the concept of a measure function. This is a rule that assigns a size to each set in a way that satisfies certain properties. For example, the measure of the empty set is 0, and the measure of a union of disjoint sets is the sum of their measures. But not all sets are measurable. Some sets resist any attempt to assign them a size in a consistent way. These are the non-measurable sets, and they are the source of some of the deepest and most perplexing problems in measure theory. Now, imagine trying to integrate a function over an interval. Without measure theory, we'd be stuck. But with it, we can define the integral in terms of the Lebesgue measure, a special kind of measure that can handle the complexities of the real numbers. In conclusion, measure theory provides a rigorous framework for dealing with size and infinity in mathematics. It underpins many areas of maths, from calculus to probability theory, and has deep philosophical implications about the nature of the infinite. So next time someone asks, how big is infinity? You can smile and say, well, that depends on how you measure it. Measure theory, a fascinating field that elegantly bridges the finite and the infinite, continues to challenge and inspire mathematicians around the world.